Welcome to lecture 2 of module 2.
In the last lecture, I have discussed on one dimensional steady state heat conduction through plane wall. In this lecture, I will discuss one dimensional steady state heat conduction in cylindrical system. So, analysis will remain more or less similar in nature, but as because the coordinate is changing, the governing equations will be changed and the boundary conditions and all these things is going to be changed, and dealing with the equations will be little different, and we will see the resistance terms are also going to be changed significantly in different way. So, as time progresses, we will see that how it happens in case of cylindrical coordinate system. So, to start with, let us first draw a typical cylinder. So, this is a hollow cylinder, and so say this is the center line and this is the length of the cylinder, say, and this cylinder has, say, this is the inner radius and this is the outer radius RO. So, this is a hollow cylinder, and say heat is conducted from inner side to the outer side. Again, if we just try to see from Fourier first law of heat conduction or Fourier's law of heat conduction, the phenomenological law, according to that Q dot R is equal to minus K A dt by dr. I am straightway writing dt by dr here, because already we have discussed these issues in case of plane wall. Now, because it is temperature is only function of r direction, it is not function of time, because it is the steady state situation we are considering, and it is not function of theta and z coordinate in the cylindrical system. Now, if we go ahead further, then what we will find is that dt by dt equals to Q dot R by this also can be written as minus K into what is the area? Area is equal to 2 pi r at any point r into L. This is the surface area. So, this is the, say, at any point r, this is r. So, 2 pi r into L, that will be the surface area through which the heat will be conducted. And one thing we should understand, that heat conduction surface area is, the surface area is perpendicular to the direction of heat conduction. So, 2 pi r L into dt by dr. Then dt is equal to or minus dt is equal to Q dot by twice pi k into L into dr by r. And now, if you do the integration, okay, say r T I to T O minus dt is equal to Q dot R by twice pi k L. Again here the k is independent of the coordinates that we are taking, and Q dot R is constant because it is the steady flow situation, steady heat conduction situation. And then it is R is equal to R I, at R is equal to R I, T is equal to T I, and R is equal to R O, that is the outside radius of the cylinder, hollow cylinder, that temperature is T O, that is the surface temperature of the hollow cylinder, and then you get dr by r. And that way, if you do see, you will be getting again, if you do the analysis now, we will be getting T I minus T O, because of the negative sign. I have changed the integration limits from T O to T I. So, T I minus T O will be equal to Q dot R by twice pi k L into ln R I R O by R I. So, this is becoming the temperature expression. So, that means what we can write is that Q R dot equals to T I minus T O by what we will write is ln R naught by R I by twice pi k into L. So, we can see that as we have seen in case of plane valve, here also you can see that numerator is the driving force for heat transfer and denominator is the resistance. So, the resistance per unit length will be that is equal to ln R naught by R I divided by twice pi k, when L is equal to 1 per unit length of the cylinder. So, now according to the electrical analog, if we see that T I is the potential at this side and T is the thermal potential in the other side, and this is the resistance, is the R is equal to ln R naught by R I divided by twice pi k into L. So, that means current flow Q dot R is equal to T I minus T O by the resistance as we have written. Now, if we change the integral limit from this, so suppose if I tell that this is equation 1. Now, in the equation 1, if we change the integral limit, like if I write from say T I to T in place of T O, any temperature T, and here it is minus d T will be equal to, as it is written, Q dot R by twice pi k L, Q dot R by twice pi k L, and then integral of dr by R, where R is equal to R I to R is equal to R. If we do the integration, then what we are going to get is that T I minus T in place of T O will be getting T I minus T, and that is equal to Q dot R by twice pi k L into ln will be getting R by R I. We had been getting R O by R I. Now, I will be getting R by R I. Now, what the idea behind is that if we now change or replace that Q dot R by twice pi k L from this side, we will get an expression for our temperature profile, and that will be like T I minus T will be equal to T I minus T O into ln R by R I divided by ln R O by R I. So, this also can be written as or T minus T I is equal to T I minus T O ln minus R by R I by ln R naught by R I. So, this way you can get that T equals to T I minus T O ln R by R I divided by ln R naught by R I. So, this becomes the temperature profile within the cylindrical body, the hollow cylinder. Now, similar expression also we can develop from the general conduction equation that we have developed previously. In the general conduction equation, we have seen that grad square T plus Q dot gen by K is equal to 1 by alpha del T by del T. Now, in this, as we said, that the one dimension and steady state without heat generation. under that situation, this equation, if we write that 1 by r, this is the grad square term, I will write del r of r del t by del r plus 1 by r square into del square t by del phi square plus del square t by del z square, that is become equal to 0. And again, as because it is one dimensional, so this part is also going 0 because it is one dimensional. And then what we find out is that 1 by r del r of r del t by del r, and that is equal to 0. From this equation, if you get, you will find t as C1 ln r plus C2. Now, putting the suitable initial condition boundary conditions like r is equal to say r I, t is equal to t I and r is equal to r O, t is equal to t O. Using these boundary conditions, we can come down to exactly the similar temperature profile, whatever we have got, that T is equal to T I minus T O by ln R O by R I into ln R by R I. So, now one thing is understood that in case of heat transfer through plane wall, we found that temperature is a linear function. When there is no heat generation term, then we have found out the temperature is a linear function of the coordinate, but in case of cylindrical coordinate, it is not, temperature is not linear function of the coordinate, and the major reason behind that, as we move in the r direction, we will see that area is continuously changing. So, we are finding that temperature is a logarithmic function of the coordinate. Okay? Now, so it is a nonlinear and logarithmic function of the coordinate. Now, if we see this is just a demonstration of getting the resistance in the cylindrical coordinate system, but in practice we will find that composite cylinders which are in place. You will see that there is a hot fluid passing through a pipe, and then outside you are putting some insulation. We have many a times we have seen that insulation is there on the pipe. If you go to any industry, chemical process industries, you will find that there are a lot of insulations being placed over the pipe. And in fact, because of the insulation, you might have seen the actual pipe size is very small, and when after the insulation, the pipe size looks to be very high, but actual pipe size is very small. So, depending upon the temperature maintained within the pipe, the insulation thickness will be changing. However, to know about the resistances, total resistances in a composite wall, let us see how it works. So, if you have a composite cylinder, so what we have is again say this is the main cylinder, cylindrical pipe, and so this is the thickness. A cylindrical pipe will have a thickness. So, this is the thickness of the cylindrical pipe, and suppose these are this is one resistance, then you may have say another resistance here. So, these are two resistances. So, if I say that this is the center point and this is say R I, this is say R 1, this is R 2 and this is say R 0. So, outside. So, this is the composite wall. So, this is, you can see that this is the front view of the composite wall of the cylinders that we are seeing into. Now, once we see this, what will be what are the resistances you have, or resistances like we can see, we can write there are the resistances belonging between R I and R 1, resistances belonging between R 1 and R 2, and resistances belonging between R 2 and R 0. So, if we write the electrical analog, we will find like this. This is one resistance, then another resistance, and then we have another resistance. So, if we say that the temperature at R I is T I, and then resistance is this one, say R 1, then this is a T 1 at the junction between R 2 and R 1 is a T 1, and this is the R 2 is the resistance, that is the resistance belonging between R 1 and R 2, and then this is temperature T 2, at this junction is the temperature T 2, and we have another resistance say R 3, and this resistance is between R 2 and R 0 in this region. And then we have finally we have got say T O outside temperature of the composite. So, under that situation, if we say, then what is R 1? R 1 is, we have already seen, and exactly similar way we have to write ln R 1 by R I by twice pi k into L. L is the length of the composite cylinder. Okay. Then R 2 will be equal to ln R 2 by R 1 by twice pi k L, and then R 3 will be equal to ln R O by R 2 divided by twice pi k into L. And then, so what will be the rate of heat transport? We can find out by, as in case of plane walls we have seen, we can write down that expression Q R dot is equal to, we can write T I minus T 1 by say R 1 will be equal to, at steady state all the things will be similar. So, we can write T 1 minus T 2 by R 2 will be equal to T 2 minus T naught by R 3, and that is equal to, again as we have seen in the previous cases, say T I minus T 2 by R 1 plus R 2, and this is equal to T 1 minus T O by R 2 plus R 3, and this is equal to T I minus T O by R 1 plus R 2 plus R 3. So, we will find out by this way, we can find out that what is the current, or by solving the different equations we have, by solving the different equations we are getting by this way under steady state conditions, we can also find out the temperature at the different junction point between the different composite walls above the or over the cylindrical body. Now, what we have discussed that heat conduction through a cylindrical composite cylindrical wall, that is a very common phenomena that we have to study, and we have to do the insulation in a pipe system so that we have to minimize the heat in leak or heat transfer or heat loss from a pipe. We have to do that. At the same time, if there is a heat generation term associated with this kind of cylindrical coordinate system, then what is going to happen? As we have seen in case of plane wall, we will see the similar kind of situations we can develop, but only thing is that here there is a difference is, like we can have a cylinder without we can have a solid cylindrical body, or we can have a hollow cylindrical body. So, if we consider the cylinder one dimensional heat transfer, okay, with heat generation, if we say, and first we will see that a solid cylindrical body so there is a possibility of heat generation. For example, if you consider the copper wire through the electrical wires, these are cylindrical in shape, and in this copper wire you have some current flowing through this. So, there is a possibility of heat generation. You know that heat generation is given by I square R T, energy generation I square R T. So, that heat is generated within the wire, and that heat will be transferred to the surroundings. So, that is some typical example, practical example of heat generation in a solid cylindrical body that we many times encounter. Now, when there is a solid cylindrical body and there is a heat generation, what will happen is that because one dimensional heat transfer, I will not write all the things. What I will write the simple form, I think by this now we have understood how to reduce the general conduction equation into simplified form. So, what I will write is 1 by R d dr. Now, I am writing not a perfect differential, I am not writing in a partial differential form, because we have taken it to be one dimensional, and also we have thought that decided in this particular discussion that it is steady state heat transfer. Okay. one dimensional, and I should say here it is a steady state, you can write steady state heat transfer. So, 1 by r ddr of r dt by dr, okay, plus q dot gen by k is equal to 0. Now, from this equation we can get that r dt by dr is equal to minus q dot gen into r square by twice k plus C 1. And then what we will get is that according to the boundary conditions at r equal to 0 and r equal to 0, dt by dr is supposed to be 0, that is the maximum condition or minima condition, and then based on that C 1 equal to 0. And therefore, finally, we can get T is equal to minus q dot gen into r square by 4 k plus C 2, and another condition if we put at r is equal to r naught, we have got T is equal to T w. So, based on that we will get that T minus T w is equal to q dot gen by 4 k into r naught square into 1 minus r by r naught whole square. So, we are lining up with this equation. So, and now condition is that maximum value of this temperature will be getting at r equal to 0. So, at r equal to 0, if we say T naught minus T w is equal to q dot gen by 4 k into r naught square, this is when r equal to 0. So, therefore, what we get is T minus T w by T naught minus T w is equal to 1 minus r by r naught whole square. So, this is what is the equation when we get when we say that a solid cylindrical body and one dimensional heat transfer with heat generation that is being happening inside the body, and the heat generation is an uniform it is taking place uniformly. Now, if you have a hollow cylindrical body, so in case of hollow cylindrical body, if we try to see, this is a similar kind of situation, same equation will be dealing with, only the boundary conditions will be changed, and the boundary conditions will be at r is equal to r I, T will be equal to T I, and r is equal to r O, T is equal to T O. Based on that, what we will find is T is equal to minus q dot gen r square by 4 k plus C 1 ln r plus C 2. That this equation, if we solve, this equation will, if we solve, will be getting this equation. And then finally, we can write that T I is equal to minus q dot gen by putting the boundary conditions r I square by 4 k plus C 1 ln r I plus C 2, and T O is equal to minus q dot gen r O square by 4 k plus C 1 ln r O plus C 2. Okay. And then we can find out that say T minus T I, and that is equal to we can write that q dot by combination of these two equations. So, the C 2 will cancel with each other, and then we will get q dot gen by 4 k into r I square. Okay, we will get 1 minus r by r I whole square, then plus C 1 ln r I if we do okay, if I T minus T O, if I do T minus okay, T minus T I only, sorry, T minus T I is equal to division r I square into r minus r I into r by r I, like this. And exactly similar way we can write T I minus T naught also to find out the value of C 1. So, if I write here T I minus T naught, then we will get Q naught Zen by 4 k into R O square into 1 minus R I by R O whole square plus C 1 ln R I by R O. So, from the two conditions of inlet and inner and outer temperature conditions, we can find out this from the expression, we can find out the value of this C 1, and this C 1 can be put over here to find out the values of temperature profile. So, for the hollow cylinder, the temperature profile is relatively different compared to the cylindrical body that we have seen. Now, through this, what we try to show is that in case of solid cylindrical body or hollow cylindrical body, when there is a one dimensional heat transfer with heat generation, what happens to the temperature profiles that we have seen. Now, if we see in the similar kind of analysis that we can continue for a hollow sphere, and for a solid sphere or hollow sphere, whatever may be the case is, we can continue similar kind of analysis. And so, to start with, consider a hollow sphere, say this is the sphere, this is say R I, and say this is R O, this is a hollow sphere, and in case of sphere, you know that exactly in the similar fashion, if we go that Q dot R is equal to minus k into area will be having 4 pi r square into dt by dr based on the Fourier equation. And then finally, if we do the integration, what we will find is that Q r dot will be equal to T I minus T O by 1 minus R I minus 1 by R O divided by 4 pi k. So, this is going to be the driving force, this is equal to driving force by this is equal to resistance. So, we can find out the resistance by this way for in case of cylindrical coordinate system. We will find out the resistance by this way, and then we can find out that temperature profile also like this. So, T minus T I, that will be equal to by 1 by R minus 1 by R I. So, in place of having that integration from R I to R O, if we do the integration from R I to R, then we will get an expression of this kind as we have seen in case of cylindrical coordinate system. And then finally, you will be having an expression of this kind T I minus T O by 1 by R I minus 1 by R O. So, by this way you can find out that T is equal to T I plus T I minus T O by 1 by R I minus 1 by R O into 1 by R minus 1 by R I. So, this is becoming the temperature profile within a sphere. Now, in case of sphere, the temperature is again we can find it is a non-linear variation, it is not a linear variation like flow through plane wall. Again, the reason behind is that the area is a continually increasing function as we go on increasing the radius of the sphere. Now, same thing we can also calculate, similar expressions we can also calculate from the general conduction equation. But before we say that, we go to that part, we will see that again the electrical analogy. If we see that electrical analogy, this is T I, this is T O, and you have this resistance, and this resistance is, we should be very careful about the resistance terms, 1 by R naught by 4 pi k. So, this becomes the resistance in case of a spherical body of a hollow spherical body, the resistance of heat transfer from R I to R O, when that thermal potential is at R I is equal to T I and R O is equal to T O. Okay. Now, exactly the similar kind of temperature profile also we can find out by, as I told you, by the general conduction equation. And general conduction equation, if we write again, that we know that grad square T plus Q dot gen by K, if you quickly see it, it will be del T by del T. And if we write that total equation, you may just go through and find out the total equation we have discussed in the previous lectures. What I will do here, I will straightway write the one dimensional form, only the radial directional form of the Gatt square term. I will write, and under there is no heat generation, so Q dot equal to 0 is the steady state, and no heat generation, and I will write that only this part, radial directional part, because the heat conduction is taking place along only along the radial direction. Then in that case, what we write is 1 by r square del r of r square del T by del r, and that is equal to 0. From here, what we can write as T is equal to minus C 1 by r plus C 2, and if we put the boundary conditions here, boundary conditions will be at r is equal to r I, T is equal to T I, and r is equal to r O, T is equal to T O. So, if you put the boundary conditions, then we can come back to our temperature expressions. Whatever we have got, T is equal to T I plus T I minus T O by 1 by r I minus 1 by r O into 1 by r minus 1 by r I. So, this is becoming the temperature profile along in a spherical vessel. Similarly, if you have a composite in a cylinder also, in a spherical vessel also, you can have a composite sphere. You may have possibilities, because this is the original sphere, this is the thickness of the spherical vessel. Now, this is the thickness of the say insulations. Like this way, we can have, as in case of cylindrical coordinate system, here also we can have several such kind of possibilities. And if you see that this is r I, this is r 1, this is r 2, and this is r 3. And if you write the electrical analog, we can understand. So, this is, there are 3 resistances between T I and T O, and in between temperatures are say T 1 and T 2. Here you have R 1, R 2 and R 3, and we know that R 1 is equal to R 1 minus R I by 4 pi k R 1 R I, then R 2 is equal to R 2 minus R 1 by 4 pi k R 1 R 2, and R 3 is equal to R 0 minus R 2 by 4 pi k R 0 R 2. So, these are the resistances, and also we can find out that Q dot R, as we have discussed previously, we can find out again from T I minus T 1 by R 1 is equal to T 1 minus T 2 by R 2 is equal to T 2 minus T 0 by R 3 is equal to T I minus T 2 by R 1 plus R 2 is equal to T 2 minus T 1 minus T 0 by R 2 plus R 3, and this is equal to T I minus T 0 by R 1 plus R 2 plus R 3. That means that this part means that is the total difference from the initial point to the final point difference by the total resistances. Okay. This is by this way we can find out the resistances, we can find out once we find out the resistances, we can find out the heat flow rates. Also, we can find out, if we are interested, we can find out the junction temperatures at different locations of the composites. Okay. Now, if we see again like a heat generation, when there is a heat generation in case of sphere, that can happen. Heat generation in a sphere is possible, and then again like a cylindrical case, we can have a hollow sphere, we can have a solid sphere. So, if we say that heat generation term, if we add in case of sphere, what we will get? We will get that 1 by r square d dr of r square dt by dr, that equation will be little bit modified as we have seen in case of cylindrical coordinate. So, this equation remains the same whether heat generation for solid sphere or in case of hollow sphere. For solid sphere, there will be a boundary condition difference, and if it is a hollow sphere, the boundary conditions will be changed. Okay. And then for solid sphere, we know that r square dt by dr is equal to minus q dot gen by 3 k into r cube plus c 1, and at r equal to 0, we know that dt by dr equal to 0, and therefore, we get t is equal to, finally we get minus q dot gen by r to the power r square by 6 k plus c 2 we get, and at r is equal to say r naught, t is equal to t w, and from that we can get that t w is equal to minus q dot gen by r square by 6 k and r naught square plus c 2. So, by this way we can find out that t minus t w is equal to q dot gen by 6 k r naught square into 1 minus r by r naught whole square. Okay. Now, exactly in the similar way we can find out the temperature profile for hollow sphere. Only thing is that here the boundary conditions will be different. R will be equal to, at r is equal to r I, T will be equal to T I, and r is equal to r O, T is equal to T O, and based on that we can find out that T is equal to minus q dot gen by 6 k into r square minus C 1 by r plus C 2, and then from there we can find out T I we can find out as a function of r I, and T O we can find out as a function of r O, just by putting the values of r is equal to r I, r is equal to r O. We put the value, we will find out the values of T I and T O, and then we will find out the similar kind of expressions, or not exactly the same thing. We will be finding out we will find out different expressions. I am sorry, we will find out the different expressions, and what we will find out is, in case of a solid sphere and is a hollow sphere. In case of solid sphere, what we get is that T max is equal to T naught, which is that is T at r equal to 0, and then what we get T max or T naught is equal to T w plus q dot gen by 6 k into r naught square, and that we get from the previous equations, and we found out the temperature profile as already we have seen T minus T w is equal to by, we can say that T naught minus T w, that is equal to 1 minus r by r naught whole square. Okay. So, this becomes the temperature profile in case of solid sphere when there is an heat generation, and we can see that it is a parabolic profile, it is a nonlinear temperature profile that is coming into picture. And in this case, in case of hollow sphere, what we have T minus T naught we can calculate, and that is equal to q dot gen by 6 k into r naught square into 1 minus r by r naught whole square plus C 1 into 1 by r naught minus 1 by r, and from T I minus T naught expression we get q dot gen by r naught square by 6 k into 1 minus r I by r naught square plus C 1 into 1 by r naught minus 1 by r I. Now, from this equation we can find out the value of C 1, because T I, T naught, r I naught all are known. If you know the values of q dot gen, we can find out the value of C 1, and this C 1 if we put here, we can get the expression of temperature. So, this way we can find out the temperature profile when there is a heat generation also in case of hollow sphere. Okay. Now, we will discuss a few problems in this. So, first problem is, it says a hot steam pipe a hot steam pipe of diameter 6 centimeter and thickness 4 millimeter has inside surface temperature (300 centigrade). It is covered with 2 layers of insulation. The first layer is 4 centimeter with thermal conductivity K is equal to 0.2 watt per meter per Kelvin, and the second layer is 2 centimeter with K is equal to 0.04. You just see that this has got much lower thermal conductivity per watt per meter per Kelvin. The outside temperature of insulation is 30 centigrade. The temperature of the insulation at the outside is, the outside temperature of insulation is 30 centigrade. Okay. Calculate the heat loss. Calculate the heat loss per meter length. Sorry. Per meter length of the pipe. Now, thermal conductivity of pipe is very high, it is 40 watt per meter per Kelvin. Compared to the insulations, the thermal conductivity is very high. So, what we understand is that we have a steam pipe, this is the central line of the pipe, it has got a certain thickness of the pipe, has got a certain thickness. Then there are some insulations which is being applied, and that insulations are 4 centimeter thick and this. So, this is 3 centimeter, this part is the thickness of the pipe is 4 millimeter, that means 0.4 centimeter. Okay. And then there is one layer of resistance. This layer of resistance is 4 centimeter, and then there is another layer of resistance, that is by insulation, this is say again 2 centimeter. This is 4. So, thus, so if we say that R I is equal to 3 centimeter and R O, say R 1 is equal to 3.4 centimeter, R 2 is equal to 3.4 plus 4, 7.4 centimeter, and R I R O is equal to say 7 plus 2, that is 9.4 centimeter. Okay. So, these are the radii. So, this has become now the size of the insulated pipe. Initially the pipe was like this, and now it has become the size of the insulated pipe. And if we try to calculate all the resistances, so R 1 will calculate as ln R 1 by R I by twice pi k, and L is taken as 1, length is equal to 1, already told, L is equal to 1 meter say. Okay. And interestingly, as these units are cancelling each other, is a ratio of these two radii. So, therefore, I am not changing the units over here, and therefore, what you get is, we will be getting ln 3.4 by 3 by twice pi k, okay, and k is equal to here, k is equal to 40. So, this value gives 4.98 into 10 to the power minus 4 Kelvin per watt. Okay. Similarly, R 2 will be ln R 2 by R 1 by twice pi k, and this is equal to ln 7.4 by 3.4 divided by 2 pi into 0.2, and this value is 0.62 Kelvin per watt. So, R 3 is equal to, we can write R 3 is equal to ln R 0 by R 2 by twice pi k, and this is equal to ln 9.4 by 7.4 divided by 2 into pi into k is equal to 0.04 for this case, and this value comes about 0.95 Kelvin per watt. Now, if we see the total resistance R T, which is equal to R 1 plus R 2 plus R 3, and this comes about, if we add up all the three, it comes about 1.5705 Kelvin per watt. And so, heat transfer rate Q dot R in the radial direction, it's becoming driving force is 300 degree centigrade minus 30 degree centigrade divided by 1.5705, that is the total resistance, and so its value is becoming 171.92 watt per meter. So, that we see that the heat transfer rate in the radial direction between the steam pipe to the environment is 171.92 watt per meter per length of this pipe. One interesting point I should tell here, the resistances whatever we have calculated, if you see the percentage resistance of the steam pipe wall, you will see that percentage resistance of the steam pipe, and this is due to the thickness of the steam pipe, and this value is R 1 by R T into 100, and if you do the calculations, you will be finding that it happens to be very small, around 0.03 percentage. So, we can see that the pipe, because you can see that the insulation, the thermal conductivity of the pipe has been 40 watt per meter per Kelvin, and so the pipe has got almost negligible resistance for the heat transfer or heat loss or heat inlet into the system. So, we have to put the insulation because of those reasons. Okay. Maybe this at this point we will stop, and we have discussed some problems related to heat conduction. We have discussed the electrical analog of heat flow with the charge flow, that is current, and we have seen how to calculate, particularly in steady state and one dimensional condition, how to get the expressions for temperature within Cartesian coordinate or within cylindrical coordinate or in spherical coordinate system. Also, we have tried to see that when there is an heat generation term involved in this in different systems, what happens to their temperature profiles, and we also have seen how to calculate through the problems, how to calculate the resistances in the different layers, and how to find out the rate of heat transfer when there is a composite wall is present over a cylinder. Similar kind of analysis, similar kind of calculations can also be done in case of spheres. So, anybody interested, they can go through several books are available in the market. You can solve the several problems. Based on that, have a practice and find out and get confidence into the subject. Thank you.